CWI Prep Course, Radiographic Testing, RT, Module 10, Part 12. Learning objectives. In this module, we're going to cover gamma rays, isotope characteristics, radioactive sources, half-life dated decay curves, radioactive source handling, radiographic testing, and advantages and disadvantages of the RT testing.
Gamma rays are produced by the nuclei of isotopes which are undergoing natural disintegration. Isotopes are varieties of the same chemical element having different atomic weights. A parent element and its isotopes all have an identical number of protons in their nuclei, but a different number of neutrons. Among the known elements, there are more than 800 isotopes, of which more than 500 are radioactive. There are natural radioactive isotopes and man-made radioactive isotopes. Radium is one of the best known and most used natural radioactive sources. Man-made radioactive sources include Cesium-137, Cobalt-60, Thulium-170, Iridium-192. The first of these is obtained as a fission byproduct. The others are obtained by neutron bombardment. Both natural and artificially produced isotopes produce gamma rays, alpha particles, and/or beta particles. Here's a slide that shows a side-by-side comparison of isotopes and their characteristics. You can see the half-lives. For cobalt, it's 5.3 years, iridium 75 days, and for cesium, it's Cesium-137, it's 30 years. But then you go down to the practical source. So you're looking at how many curies it's kicking off. So the Cobalt-60 is kicking off 20 curies. Iridium-192 is kicking off 50, and Cesium-137 is kicking off 75. So the iridium has a half-life of 75 days. So with iridium, after 75 days, you're down to 25 curies. With cesium, after 75 days, you're still at 75 curies. So just kind of giving you a side-by-side look at what the half-life does to how much radiation is being kicked off, and also a side-by-side look at the half-lives of the various isotopes and their characteristics. Radioactive sources, Cobalt-60. Cobalt-60 is an artificial isotope created by neutron bombardment of cobalt. Having a half-life of 5.3 years, Cobalt-60 primary gamma ray emission consists of 1.33 and 1.17 MeV rays, similar in energy content to the output of a 2 MeV X-ray machine. The radioisotope is supplied in the form of a capsulated pellet and may be obtained in different sizes. It is used for radiography of steel, copper, brass, and other medium weight metals of thicknesses ranging from 1 to 8 inches. Because of its penetrating radiation, its use requires thick shielding with resultant weight and handling difficulty. Radioactive sources, Iridium-192. Iridium-192, another artificial isotope produced by neutron bombardment, has a half-life of approximately 75 days. It has a high specific activity and emits gamma rays of 0.31, 0.47, and 0.60 MeV, comparable in penetrating power to those of a 600 kilovolt P X-ray machine. Industrial, it is used for radiography of steel and similar metals of a thickness between 2.5 and 3 inches. Its relatively low energy radiation and its high specific activity combine to make it easily shielded strong radiation source of small physical size and focal spot. The radioisotope is obtainable in the form of a capsulated pellet. Cesium-137, a byproduct of the fission process, has a half-life of 30 years. It emits gamma rays of 0.66 MeV, equivalent in energy to the radiation of a 1 MeV X-ray machine. It is used in the radiography of steel thicknesses between 1 and 2.5 inches. It is superior to other isotopes of similar capability, only in its slow rate of decay. Cesium-137 is usually handled in the form of the chloride, cesium chloride, a soluble powder requiring special safety precautions. The U.S. Nuclear Regulatory Commission recommends double encapsulation in containers constructed of silver-brazed stainless steel. Half-life. Half-life is the length of time required for the activity of a radioisotope to decay, disintegrate, to 1/2 of its initial strength is termed half-life. The half-life of a radioactive isotope is a basic characteristic and is dependent upon the particular isotope of a given element. In radiography, the half-life of a gamma source is used as a measure of the activity in relation to time, and dated decay curves similar to that shown in figure 5.2.8 are supplied with radioisotopes upon procurement. Radioactive decay follows an exponential relationship, and therefore a straight line plot occurs on a semi-log graph as shown in 5.2.8. So this is the half-life of Cobalt 60. It's got a half-life of 5.27 years, and it shows you, okay, so if you start out with, a chunk of it, let's call it 1 pound, then after one half-life, in 5 years, you're going to have 1/2 pound. And instead of emitting 30 curies like you were at the start, you're going to be kicking off 15. And then, 5 years later, you're down from 15 to 7.5, and then 375. So you can see how this decay works. It's a half-life. And you can see why this would be a problem for, some things that are radioactive waste that have a half-life of thousands of years. So in 10,000 years, you're going to be down to half the amount that you have left. But anyways, this comes into play with the half-life because on things like Iridium 192, where you have a half-life of 73 days, you lose a lot of your power on how well you can, or how much radiation you're able to generate. It'd be like having a car. You start out with 8 cylinders, and then after 6 months, you're down to 4 cylinders, and then you're down to 2 cylinders, and then you're down to 1 cylinder. It's kind of how this works. So that's why when they're choosing their radioactive sources, there's a whole bunch of different variables that come into play there. But this is the half-life of Cobalt 60. So here's the half-life of Iridium 192, which is 73.83 days. So you can see it decays pretty quick. You start out with 1 pound of it, and within 2 years, you're down to almost nothing left. So if you're going to shoot with this stuff, you're not buying this as a long-term investment. This radiation source is pretty short-lived. So you just have to keep that in mind. But that's what they're talking about when they talk about half-lives. And this is, you can see the difference between Iridium 192 and the Cobalt 60, which had a 5-year half-life. Here's the half-life of Cesium-137. It's got a half-life of 30 years. And this was a bunch of the stuff that got kicked into the atmosphere when the Fukushima disaster happened over in Japan. So you can see why they're pretty worried about it. It doesn't have a half-life of 73 days like Iridium, where it would all be basically burned up and gone by now and gone into a different type of radioisotope. Cesium-137, after 30 years, you're down to half of it. 60 years, you're down to, 25% of what you started with. But depending on how messed up things were, like over in Japan, you still could be kicking off a considerable amount of radiation. So it could take, over there, it could take a century or two for this stuff to completely dissipate. And you look at this from a standpoint of a half-life of something you're going to use to do radiography. Well, with a 30-year half-life, you can do a lot of x-rays before you, or you can do a lot of radiography before you even get down to 50% of your half-life. So even at 30 years, you're down to 50%. 60 years, you're down to 25%. It's like I said, it's a big difference from Iridium and even from Cobalt with its 5.27 years of half-life. Okay, here we've got a half-life dated decay curve, and this is same information as I gave you before, but it's just giving you the same information but a different format. But you can see your activity in curies on the y-axis, and on the x-axis is time. So our half-life for this material, Cobalt 60, is 5.27 years. So you can see at July 1st, 1965, you've got 30 curies of activity. Then 5 years later, on July 1st, 1970, you're down to about 15 curies of activity. And it just keeps going like that. And this is important for people that shoot x-rays because, or shoot, that do radiography. Because of the ever-present radiation hazard, isotope sources must be handled with extreme care and stored and locked in adequately shielded containers when not in use. Equipment to accomplish safe handling and storage of isotope sources together with a source is called a camera. This is what they use to shoot if you're out on a site, if you're not using a different method. Radiographic testing, advantages and disadvantages. Advantages: good internal inspection method. Excellent geometric representations, good sensitivity, 2% is reasonable. Small details are visible. The limit is often the size of the grains on the film being used. Disadvantages: the image is a shadow only. The shadow varies only as the amount of or density of the material varies. Therefore, it can see missing material, but if a delamination exists perpendicular to the X-ray beam with material pulled apart but not missing, an X-ray will not detect it. Sometimes expensive in time, labor, and facilities, and you have the personnel safety requirements because you're bouncing radiation through things to get a look at things. So you have issues that you need to deal with there.
Summary: in this module we covered gamma rays, isotope characteristics, radioactive sources, half-life, dated decay curves, radioactive source handling, radioactive testing, RT advantages, disadvantages.